Okay, hey guys, so today we're going to be talking about Gibbs free energy. Okay, so to begin, let's just remember that the second law of thermodynamics says that the entropy of the universe is always increasing, right? So that's referring to delta S of the universe equals delta S of the system and delta S of the surroundings. And something that's like spontaneous or that's favorable, usually the total delta S of the universe is greater than 0, right? So delta S universe has to be greater than 0 for a reaction to occur. But the problem is that we can't always calculate the amount of disorder in the universe, right? That's like, it's not reasonable. So scientists are really concerned with just the delta S of the system. So it's the spontaneity of the system. And that's referred to as Gibbs free energy. So we're just talking about how spontaneous the system is. Right, so spontaneity of a reaction, how likely that reaction will go forward. So Gibbs free energy is written as delta G. So this is at a constant temperature and pressure. The change in Gibbs free energy is defined in an equation, and that equation is delta G. Again, we're talking about the system, equals delta H, which is the enthalpy, again, of the system, minus temperature, and then delta S, again, of just the system. So we're just looking at changes within the system, because we're not really concerned with what's going on in the universe so much as what's going on in the reaction. So a great way to remember this equation is goldfish are horrible without tartar sauce, right? So let's see. Goldfish, right, delta G, are horrible, H, delta H, without tartar sauce, T, and S. So that's a great way to remember this equation. Okay, and so as we know, delta H is change in enthalpy, delta S is change in entropy, and this is all talking about the system. So this is actually a great kind of chart to take a look at, and it'll tell you if a reaction will go forward or not, and technically delta G, okay, let's backtrack for a second. Delta S overall, right, in the universe should be greater than 0 for something to occur. It's the opposite for delta G, for Gibbs free energy. You want it to be less than 0 for a reaction to be considered favorable. So if you have a negative delta H, and this is we're talking about in this equation. This equation, delta H. Right. So if this delta H is negative, and this one is positive, delta S is positive, then your delta G will always be negative. And that's how you know that your reaction is always favored. So that reaction will always move forward. Now, if your delta H is positive, meaning it's endothermic, and the entropy of the system is negative, so your entropy actually decreases, then your delta G will be positive, and it's never favored. So that'll never go forward. Then we have, if your delta H is negative, it's exothermic, and your delta S the entropy is decreasing. Well, then this gets a little bit more complicated. It depends on the temperature, because as the temperature increases, your delta G will become more positive, and the reaction will become less favored. And remember, T T is measured in kelvins. In kelvins, it's always going to be a positive number, right? Because when T equals 0 kelvins is like absolute 0. And it can't be colder than that. So this quantity here will always be positive. So now let's say that you have an endothermic equation and the delta S is positive, so the entropy is increasing. Again, it depends on the temperature, and as you increase the temperature, then your delta G will become more negative and the reaction will become more favored. So yeah. And remember that exothermic is more favored in terms of delta H, and as entropy increases, that's also more favored. So this is why this reaction is always favored. Okay, so kind of just to repeat what I just I said, when delta G is, let's see, less than 0, the reaction will proceed forward, or we can say it'll proceed spontaneously. So that means that reaction will happen. Now, if you calculate it using that equation and your delta G is greater than 0, then the reaction is not spontaneous and it'll actually move in the reverse direction. So it'll actually go, in the reverse direction, and it is not spontaneous. Okay, and the last one, if your delta G is equal to 0, then your system is in equilibrium. And the concentration of your products and reactants, so let's say products, will remain constant. So concentration of products and reactants are constant. Okay. And another way to know, maybe a better way of looking at that chart that I have pulled up, would be to write it out like this. So if your delta H is less than 0 and your delta S is greater than 0, then the reaction is spontaneous at all temperatures, right? So that means your, let's see, better color here, your delta G is less than 0, right? Because we want a negative delta G. And then let's say your delta H is greater than 0 and your delta S is also greater than 0. That is spontaneous at a high temperature. So when your T delta S is large. Right, so your T delta S is in that, I'm referring to that equation. The goldfish are horrible without tartar sauce equation, so let's see, that is, here I can write it out. Delta G of the system equals delta H of the system minus T delta S. And this is what I'm referring to right here. Okay. Now let's say your delta H is less than 0 and your delta S is also less than 0. So that's spontaneous at low temperature when your T delta S is small. Okay, and the last one is when your delta H is greater than 0 and your delta S is less than 0. That's not spontaneous. Not spontaneous at all temperatures, and your delta G is positive, it's greater than 0. These are kind of the 4 situations, scenarios that describe the delta G of the system, the spontaneity of the system, whether that reaction is favorable or not.